Hey, alright, so today we are studying chapter 4 of the System Design Interview book, Design a Rate Limiter. Alright, so in the past three chapters, we have gone over how we are supposed to prepare for the interview, what are the basic latency numbers, and other things related to that. So, yeah, in this chapter, we pick up a real world system and we break it down how does it work and how we are supposed to design it. So yeah, let's get started. In a network system, a rate limiter is used to control the rate of traffic sent by a client or a service. In the HTTP world, a rate limiter limits the number of client requests allowed to be sent over a specified period. If the API request count exceeds the threshold defined by the rate limiter, all the access calls are blocked. Here are few examples. A user can write no more than 2 posts per second. Alright. So if the API request count exceeds the threshold defined by the rate limiter, all the access calls are blocked. Here are a few examples. A user can write no more than 2 posts per second. You can create a maximum of 10 accounts per day from the same IP address. And you can claim rewards no more than 5 times per week from the same device. Okay, so yeah, those are some of the examples where you might want to have a rate limiter in your app. Okay, moving on. In this chapter, you are asked to design a rate limiter. Before starting the design, we first look at the benefits of using an API rate limiter. Prevent resource starvation caused by DOS attacks. Almost all APIs published by large tech companies enforce some form of rate limiting. For example, Twitter limits the number of tweets to 300 per 3 hours. Google Docs APIs have the following default limit: 300 per user per 60 seconds for read requests. A rate limiter prevents DOS attacks, either intentional or unintentional, by blocking the excess calls. Reduce cost. Limiting excess requests means fewer servers and allocating more resources to high priority APIs. Okay. Rate limiting is extremely important for companies that use third party APIs. For example, you are charged on a per call basis for the following external APIs: check credit, make a payment, retrieve health records, etc. Limiting the number of calls is essential to reduce costs. Okay, makes sense so far. Prevent servers from being overloaded. To reduce server load, a rate limiter is used to filter out excess requests caused by bots or users' misbehavior. Alright. Prevent servers from being overloaded, to reduce server load, and to prevent excess requests caused by bots or users' misbehavior. Alright. Step 1. Understand the problem and establish design scope. Rate limiting can be implemented using different algorithms, each with its own pros and cons. The interactions between an interviewer and a candidate helps to clarify the type of rate limiters we are trying to build. Candidate, what kind of rate limiter are we going to design? Is it a client-side rate limiter or server-side API rate limiter? Great question. We focus on the server-side API rate limiter. All right. Candidate, does the rate limiter throttle API requests based on IP, the user ID, or other properties? Interviewer, the rate limiter should be flexible enough to support different sets of throttle rules. Candidate, what is the scale of the system? Is it built for a startup or a big company with a large user base? Interviewer, the system must be able to handle large number of requests. Candidate, will the system work in a distributed environment? Interviewer, yes. Candidate, is the rate limiter a separate service or should it be implemented in application code? Interviewer, it is a design decision up to you. Candidate, do we need to inform users who are throttled? Interviewer, yes. So finally, here is a summary of the requirements for the system. Accurately limit Excessive requests, low latency. The rate limiter should not slow down HTTP response time. Use as little memory as possible. Distributed rate limiting. The rate limiter can be shared across multiple servers or processes. Exception handling. Show clear exceptions to users when their requests are throttled. High fault tolerance. If there are any problems with the rate limiter, for example, a cache server goes offline, it does not affect the entire system. Alright. Step 2. Propose high level design and get buy-in. Okay, we have established the design scope. Now we will move towards proposing high level design and getting a buy-in from the interviewer. Okay. Let us keep things simple and use a basic client and server model for communication. Where to put the rate limiter? Intuitively, you can implement a rate limiter at either the client or server side. Client side implementation, generally speaking, client is an unreliable place to enforce rate limiting because client requests can easily be forged by malicious actors. Moreover, we might not have control over the client implementation. Okay, so the reason we do not want it on the client side is it can be modified and we do not have control over how they are implementing it. Okay, makes sense. So server side implementation. Figure below shows a rate limiter that is placed on the server side. Alright. Besides the client and server side implementation, there is an alternative way. Instead of putting a rate limiter at the API servers, we create a rate limiter middleware which throttles requests to your APIs as shown in the figure below. So we have client, then there is a rate limiter, and after that it is where the API servers come in. Alright. So let us use an example in figure below to illustrate how rate limiting works in this design. Assume our API allows 2 requests per second and a client sends 3 requests to the server within a second. Okay. The first 2 requests are routed to API servers. However, the rate limiter middleware throttles the third request and returns a HTTP status code to 429. The HTTP 429 response code indicates a user has sent too many requests. Alright. So client sent first 2 requests, they went to the API server. The third one was returned without 429. Okay. Cloud microservices have become widely popular, and rate limiting is usually implemented within a component called API Gateway. API Gateway is a fully managed service that supports rate limiting, SSL termination, authentication, IP whitelisting, servicing static content, etc. For now, we only need to know that the API Gateway is a middleware that supports rate limiting. Okay. While designing a rate limiter, an important question to ask ourselves is where should the rate limiter be implemented, on the server side or in a gateway? There is no absolute answer. It depends on your company's current tech stack, engineering resources, priorities, goals, etc. Here are a few general guidelines. Evaluate your current technology stack, such as programming language, cache service, etc. Make sure your current programming language is efficient to implement rate limiting on the server side. Identify the rate limiting algorithm that fits your business needs. When you implement everything on the server side, you have full control of the algorithm. However, your choice might be limited if you use a third party gateway. If you have already used microservice architecture and included an API gateway in the design to perform authentication, IP whitelisting, etc., you may add a rate limiter to the API gateway. Building your own rate limiting service takes time. If you do not have enough engineering resources to implement a rate limiter, a commercial API gateway is a better option. Alright. Algorithms for rate limiting. Rate limiting can be implemented using different algorithms, and each of them has distinct pros and cons. Even though this chapter does not focus on algorithms, understanding them at high level helps to choose the right algorithm or combination of algorithms to fit our use cases. Here's a list of popular algorithms: token bucket, leaking bucket, fixed window counter, sliding window log, sliding window counter. Okay. Token bucket algorithm. The token bucket algorithm is widely used for rate limiting. It is simple, well understood, and commonly used by internet companies. Both Amazon and Stripe use this algorithm to throttle their API requests. The token bucket algorithm works as follows. A token bucket is a container that has a predefined capacity. Tokens are put in the bucket at preset rates periodically. Once the bucket is full, no more tokens are added. As shown in figure below, the token bucket capacity is 4. The refiller puts 2 tokens into the bucket every second. Once the bucket is full, extra tokens will overflow. Each request consumes 1 token. When a request arrives, we check if there are enough tokens in the bucket. Figure below explains how it works. If there are enough tokens, we take 1 token out for each request and the request goes through. If there are not enough tokens, the request is dropped. So we have a set of requests here. Alright, let me get the pen. Yeah. So we have a set of requests here, and then there's the refiller that is putting 3 requests per second, and then we check if there are enough tokens or not. If there are enough tokens, then we forward the requests. If there are not enough tokens, then we drop the request. Okay, so that's how that works. Okay, so figure below illustrates how token consumption, refill, and rate limiting logic works. In this example, the token bucket size is 4 and the rate refill rate is 4 per minute. Okay, so yeah, how this would work is basically you have requests coming in and you start with 4 tokens. Then one request comes in, so then you are left with 3 tokens. One token is consumed. Then we start with 3 tokens. All the 3 requests will go through. Yeah, makes sense. 3 tokens are consumed. And look at the time also. On the fifth second, that on the first 0 0, it's like after the first minute when you start, the first request comes in. After 5 seconds, the second request comes in. And we have a rate limiting of 20 per second, right? So this will keep dropping all the requests that come till the 1 minute window is over. At first minute, 4 tokens are refilled at 1 minute interval. Yeah, so that's how this would work. Okay, moving on. The token bucket algorithm takes 2 parameters: bucket size, the maximum number of tokens allowed in the bucket; refill rate, number of tokens put into bucket every second. Okay, how many buckets do we need? This varies and it depends on the rate limiting rules. Here are a few examples. It is usually necessary to have different buckets for different API endpoints. For instance, if a user is allowed to make 1 post per second, add 150 prints per day, and like 5 posts per second, 3 buckets are required for each user. If we need to throttle requests based on IP address, then each IP address requires a bucket. If the system allows a maximum of 10,000 requests per second, it makes sense to have a global bucket shared by all requests. Pros: the algorithm is easy to implement, memory efficient. Token bucket allows a burst of traffic for short periods. A request can go through as long as there are tokens left. Cons. Two parameters in the algorithm are bucket size and token refill rate. However, it might be challenging to tune them properly. Leaking bucket algorithm. The leaking bucket algorithm is similar to the token bucket except that requests are processed at a fixed rate. It is usually implemented with a first in first out FIFO queue. The algorithm works as follows. When a request arrives, the system checks if the queue is full. If it is not, the request is added to the queue. Otherwise, the request is dropped. Requests are pulled from the queue and processed at regular intervals. Okay, so this is the request. Bucket is full or not. If it is not, then we, okay, go to the queue and add it and then we process it. That's what it means by saying requests go through. If the bucket is full, then we drop the requests. Okay, understood. Fair. Leaking bucket algorithm takes the following two parameters. Bucket size, it is equal to the queue size. The queue holds the requests to be processed at a fixed rate. Outflow rate, it defines how many requests can be processed at a fixed rate, usually in seconds. Shopify, an e-commerce company, uses leaky buckets for rate limiting. Pros, memory efficient given the limited queue size. Alright. Requests are processed at a fixed rate, therefore it is suitable for use cases that a stable outflow rate is needed. Cons. A burst of traffic fills up the queue with old requests, and if they are not processed in time, recent requests will be rate limited. There are two parameters in the algorithm. It might not be easy to tune them properly. Fixed window counter algorithm. Fixed window counter algorithm works as follows. The algorithm divides the timeline into fixed sized time windows and assign a counter for each window. Each request increments the counter one by one. Once the counter reaches the predefined threshold, new requests are dropped until a new time window starts. Each request increment, okay. Once the counter reaches the predefined, new requests are dropped, okay. Let us use a concrete example to see how it works. In figure below, the time unit is 1 second and the system allows a maximum of 3 requests per second, okay. In each second window, if more than 3 requests are received, extra requests are dropped as shown in the figure below. Okay, on the first minute we got 3 requests, it was allowed. On the first hour, first second, we got 6, 3 were accepted, other were dropped. We got 4, 3 accepted, 1 dropped. Got 2, all accepted. Got 5, 3 accepted, 2 dropped. A major problem with this algorithm is that a burst of traffic at the edges of time windows could cause more requests than allowed quota to go through. Consider the following case. In the figure above, the system allows a maximum of 5 requests per minute, and the available quota resets at human-friendly round minute. As seen, there are 5 requests between 2 or 1 minute, 2 or 00 and 2 1. Okay, 201. Alright. And 5 more requests between 201 and 202. For the 1 minute window between 2030, for the 1 minute window between 2030 and to 130. Oh, okay, okay, okay. This is the window. All right. This is 200. This is 202. This is 201. So between 2030 and 202. Okay, understood. So it is saying understood. I think I get what they are saying. They are saying a major problem with this algorithm is that burst of traffic at the edges of time windows. This is an edge of 201 mark. This is an edge of 200 mark. and this is 202. Okay, so they are trying to say at the edges of time windows, it could cause more requests than allowed quota to go through. So here, if the idea of implementing this was something like this, that during this window and during this window, you get 5 requests each. But what has happened was till 2030, that is 30th second, no requests came. Then 5 came in this time window, and then 5 came in this time window. So independently, if you look second between 0 to first minute, 5 requests came, and between first minute to second minute there are other 5 requests. But if you like zoom in a bit more, then you would see that from 30th second of the 0 to 1 mark and between the first 30 seconds of first to second mark, with that duration is also 1 minute. Like if you see, this whole is also 1 minute, but this is in violation of the policy because 5 requests per minute are needed, but we are seeing that 10 have gone through. All right. So yeah, that was it. Okay. That is twice as many allowed requests. Okay, correct. So moving on. Pros. It is memory efficient, easy to understand, resetting available quota at the end of a unit time window fits certain use cases. Okay. Cons. Cons. Spike in traffic at the edges of a window could cause more requests than the allowed quota to go through, as we saw above. Okay, sliding window log algorithm. As discussed previously, the fixed window counter algorithm has a major issue. It allows more requests to go through at the edges of a window. The sliding window log algorithm fixes this issue. It works as follows. The algorithm keeps track of request timestamps. Timestamp data is usually kept in cache, such as sorted set of Redis. Alright. When a new request comes in, remove all the outdated timestamps. Outdated timestamps are defined as those older than the start of the current time window. Okay. Add timestamp of the new request to the log. If the log size is the same or lower than the allowed count, a request is accepted. Otherwise, it is rejected. We explain the algorithm with an example below. Policy is of allow 2 requests per minute. On the first second, we get 1 request, it is accepted. On the 30th second, we get a request that is accepted. On the 50th second, when we get another request that is rejected. And first and 30th are already served. And last timestamp that we store is 50. So, yeah. And then after a minute 40, when a request comes in at minute 40, it checks that the last call came at 50th second and it is within the permissible limit, so it allows it. In this example, the rate limiter allows 2 requests per minute. Usually, Linux timestamps are stored in the log. However, human readable presentation of time is used in our example for better readability. The log is empty when a new request arrives at first second, thus the request is allowed. A new request arrives at 30th second, the timestamp 30 is inserted into the log. After the insertion, the log size is 2, not larger than the allowed count. Thus the request is allowed. A new request arrives at 50th second and timestamp is inserted into the log. After the insertion, the log size is 3, larger than the allowed size 2. Therefore, this request is rejected even though the timestamp remains in the log. A new request arrives at 1st minute 40th second. Requests in the range of 1 minute 40 to 1 minute to 0 minute 40 second to 1 minute 40 second are within the last time frame, but requests sent before 0 minute 40 seconds are outdated. Two outdated timestamps, that is, first second and 30th second, are removed from the log. After the remove operation, the log size becomes 2, therefore the request is accepted. Pros: rate limiting implemented by this algorithm is very accurate. In any rolling window, requests will not exceed the current rate limit. Cons: the algorithm consumes a lot of memory because even if a request is rejected, its timestamp will still be stored in the memory. Sliding window counter algorithm. The sliding window counter algorithm is a hybrid approach that combines the fixed window counter and sliding window log. The algorithm can be implemented by two different approaches. We will explain one implementation in this section and provide reference for the other implementation at the end of the section. Figure below illustrates how this algorithm works. Number of requests on the y-axis, time is on the x-axis, and we have a window and there is a rate limit of 5 requests per minute. Assume the rate limiter allows a maximum of 7 requests per minute, and there are 5 requests in the previous minute and 3 in the current minute. For a new request that arrives at a 30% position in the current minute, the number of requests in the rolling window is calculated using the following formula: requests in current window plus requests in previous window into overlap percentage of the rolling window and previous window. Using this formula, we get 3 plus 5 into zero point 0.7 equals to 6.5 requests. Depending on the use case, the number can either be rounded up or down. In our example, it is rounded down to 6. Since the rate limiter allows a maximum of 7 requests per minute, the current request can go through. However, the limit will be reached after receiving one more request. Due to space limitation, we will not discuss the other implementation here. Instead, readers should refer to the reference material. This algorithm is not perfect. It has pros and cons. It smooths out spikes in traffic because the rate is based on the average rate of the previous window. It is memory efficient. Cons: it works for no strict lookback window. It is an approximation of the actual rate because it assumes requests in the previous window are evenly distributed. However, this problem may not be as bad as it seems. According to experiments done by Cloudflare, only 0.003% of requests are wrongly allowed or rate limited among 400 million requests. High level architecture. The basic idea of rate limiting algorithms is simple. At the high level, we need a counter to keep track of how many requests are sent from the same user or IP address or a basis whatever criteria of user ID or something else you are using. If the counter is larger than the limit, the request is disallowed. Where shall we store counters? Using the database is not a good idea due to slowness of disk access. In-memory cache is chosen because it is fast and supports time-based expiration strategy. For instance, Redis is a popular option to implement rate limiting. It is an in-memory store that offers two commands, incr and expire. incr, it increases the stored counter by 1. Expire, it sets a timeout for the counter. If the timeout expires, the counter is automatically deleted. Figure below shows the high level architecture for rate limiting, and this works as follows. Client makes a call. It hits the rate limiter middleware. Then a check happens for the limit on Redis. If it is allowed, then it goes to API servers. The client sends a request to rate limiting middleware. Rate limiting middleware fetches the counter from the corresponding bucket in Redis and checks if the limit is reached or not. If the limit is reached, the request is rejected. If the limit is not reached, the request is sent to API servers. Meanwhile, the system increments the counter and saves it back to Redis. Step 3. Design deep dive. The high level design in figure 412 above does not answer the following questions. How are rate limiting rules created? Where are the rules stored? How to handle requests that are rate limited? In this section, we will first answer the questions regarding rate limiting rules and then go over the strategies to handle rate limited requests. Finally, we will discuss rate limiting in distributed environment, a detailed design, performance optimization, and monitoring. Rate limiting rules. Lyft open sourced their rate limiting components. We will peek inside of the component and look at some examples of rate limiting rules. Domain, messaging, descriptors, message type, value, marketing. Rate limit unit day, requests per unit 5. In the above example, domain messaging, okay. E message type, value marketing, rate limit unit day, requests per unit 5. So 5 requests per day is what they are allowing. In the above example, the system is configured to allow a maximum of 5 marketing messages per day. Here is another example, domain auth, descriptors auth type, value login, rate limit, unit, minute, requests per unit 5. This rule shows that clients are not allowed to log in more than 5 times in 1 minute. Rules are generally written in configuration files and saved on disk. Exceeding the rate limit. In case a request is rate limited, APIs return a HTTP response code 429 too many requests to the client. Depending on the use cases, we may enqueue the rate limited request to be processed later. For example, if some orders are rate limited due to system overload, we may keep those orders to be processed later. Rate limiter headers. How does a client know whether it is being throttled? And how does a client know the number of allowed remaining requests before being throttled? The answer lies in HTTP response headers. The rate limiter returns the following HTTP headers to the clients. X rate limit remaining, the remaining number of allowed requests within the window. X rate limit, it indicates how many calls the client can make per time window. X rate limit retry after, the number of seconds to wait until you can make a request again without being throttled. When a user has sent too many requests, a 429 too many requests error and X rate limit retry after header are returned to the client. Detailed design. Figure below represents a detailed design of the system. Client. Rules are stored on the disk. Workers frequently pull rules from the disk and store them in a cache. Okay, cached rules are stored here. When a client sends a request to the server, the request is sent to the rate limiter middleware first. Alright. Rate limiter middleware loads rules from the cache. Okay. The rules. So basically, when a client. Okay. Okay. Rules. Fetches the rules here. It fetches counters and last request timestamp from Redis cache. Okay. Fetch done. Based on the response, the rate limiter decides if the request is not rate limited, it is forwarded to the API servers. So in the happy case, okay. If the request is rate limited, the rate limiter returns 429, too many requests, error to the client. In the meantime, the request is either dropped, or forwarded to a queue. Say this would be some sort of DLQ or whatever, where you can resume or consume from later on. This is sent to the client back, that 429 along with the response headers we talked about. Alright. Rate limiter in a distributed environment. Building a rate limiter that works in a single server environment is not difficult. However, scaling the system to support multiple servers and concurrent threads is a different story. Okay. There are two challenges: race condition and the synchronization issue. Race condition. As discussed earlier, rate limiter work as follows at the high level. Read the counter value from Redis. Check if counter plus 1 exceeds the threshold. If not, increment the counter by value 1 in Redis. Race conditions can happen in a highly concurrent environment as shown in figure below. Original counter value 3, request 1, read counter. Okay, check and increment counter value 4, request 2. Okay, so by the time it was reading the counter and before it incremented, request 2 also called read and counter value stored as 4. Instead, it should be 5. Assume the counter value in Redis is 3. If two requests concurrently read the counter value before either of them writes the value back, each will increment the counter by 1 and write it back without checking the other thread. Both request threads believe they have the correct counter value. However, the correct value should be 5. Okay. Locks are the most obvious solution for solving this condition. Before you do a read, you take a lock on the counter value, then you read, then you increment, and then you release the lock so that other thread can take it. But locks will significantly slow down the system. Okay. Two strategies are commonly used to solve the problem: Lua script uh, and sorted set data structure in Redis. For readers interested in these strategies, refer to corresponding reference materials. Synchronization issue. Synchronization is another important factor to consider in a distributed environment. To support millions of users, one rate limiter server might not be enough to handle the traffic. When multiple rate limiter servers are used, synchronization is required. For example, on the left side of figure below, client 1 sends request to rate limiter 1 and client 2 sends requests to rate limiter 2. Alright, as the web tier is stateless, clients can send requests to a different rate limiter as shown on the right side of figure 415. If no synchronization happens, rate limiter 1 does not contain any data about client 2. Okay, thus the rate limiter cannot work properly. One possible solution is to use sticky sessions that allow a client to send traffic to the same rate limiter. The solution is not advisable because it is neither scalable nor flexible. A better approach is to use centralized data store like Redis. The design is shown below. Client 1 and client 2, both values will go to a Redis and will be fetched from there onwards. Okay. Performance optimization. Performance optimization is a common topic in system design interviews. We will cover two areas to improve this. Okay. First, multi-data center setup is crucial for a rate limiter because latency is high for users located far away from the data center. Most cloud service providers build many edge server locations around the world. For example, as of 20th May 2020, Cloudflare has 194 geographically distributed edge servers. Traffic is automatically routed to the closest edge server to reduce latency. Second, Synchronize data with an eventual consistency model. If you are unclear about the eventual consistency model, refer to the consistency section in chapter 6. Design a key value store. Monitoring. After the rate limiter is put in place, it is important to gather analytics data to check whether the rate limiter is effective. Primarily, we want to make sure the rate limiting algorithm is effective. The rate limiting rules are effective. For example, if rate limiting rules are too strict, many valid requests are dropped. In this case, we want to relax the rules a little bit. In another example, we notice our rate limiter becomes ineffective when there is a sudden increase in traffic like flash sales. In this scenario, we may replace the algorithm to support burst traffic. Token bucket is a good fit here. Step 4. Wrap up. In this chapter, we discussed different algorithms of rate limiting and their pros and cons. Algorithms discussed include token bucket, leaking bucket, fixed window, sliding window log, sliding window counter. Then we discussed the system architecture, rate limiter in a distributed environment, performance optimization, and monitoring. Similar to any system design interview questions, there are additional talking points you can mention if time allows. Hard versus soft rate limiting. Hard, the number of requests cannot exceed the threshold. Soft, requests can exceed the threshold for a shorter time period. Rate limiting at different levels. In this chapter, we only talked about rate limiting at the application level, that is HTTP, which is the layer 7 on the OSI network model. Okay, it is possible to apply rate limiting at other layers. For example, you can apply rate limiting by IP address using IP tables, that is layer 3. The Open Systems Interconnect model, OSI model, has 7 layers. Layer 1 physical layer, layer 2 data link layer, layer 3 network layer, layer 4 transport layer, layer 5 session layer, layer 6 presentation, and layer 7 application. Avoid being rate limited. Design your client with best practices. Use client cache to avoid making frequent API calls. Understand the limit and do not spend too many requests. Do not send too many requests in a short time frame. Include code to catch exceptions or errors so your client can gracefully recover from exceptions. Add sufficient backup time to retry logic. Congratulations on getting this far. Now give yourself a pat on the back. Good job. Alright, so that is chapter 4 of the book. We have gone over how do you design a rate limiter, what are the different algorithms during it, how do you do the monitoring on it, how do you have a eventual consistency model, performance optimization, how does that look like, what are the issues with the race condition in a distributed environment on a rate limiter, how, where are rules stored, how a cache is used, and how would the call go for your how would the call go for your rate limiter. And then we have gone over how Lyft has defined the rate limiting rules, what happens when we exceed the rate limit, what are the commonly known headers that are to be sent from the server to the client. Yeah, so that was it. And then all of the different algorithms that are used, sliding window counter, sliding window log, then fixed window counter, leaky bucket, token bucket, and so on. So, yeah, that was chapter 4 of the system design interview book. How would you go on about it? How would you use the API gateway to write it? And things like that. How do you define the scope? And then how do you propose high level design? How do you go into various algorithms and so on about this? So, yeah, that was all for the chapter 4 of the book, and we will be back soon with another video. All right, thanks a lot.